Architecting a real-time navigation system for 1 billion daily active users is an exercise in absolute extreme scale. To see how Google Maps survives this load, we'll contrast a hardened architecture against a naive server cluster. A common instinct is forcing clients to send a GPS ping every second, while the backend attempts dynamic, real-time map rendering. For this design exercise, our scope is limited to 3 core features: user location updates, accurate navigation services, and map rendering. The system must maintain high availability and accurate routing with near-zero latency and minimal battery drain. Demanding 1-second server synchronization essentially weaponizes a billion user devices, turning them into a massive DDoS attack against your own infrastructure. The mathematical reality of our user base proves why that approach fails. We assume 1 billion users interact with the app for approximately 35 minutes per week. If the system accepts a GPS ping every second from those users, it generates an average load of 3 million queries per second. Factoring in rush hour traffic causes that load to spike to 15 million. No standard database handles 15 million concurrent write locks. We must aggressively neutralize this specific bottleneck. This globe represents our first major engineering requirement, translating the physical geometry of the world onto a mobile screen. This requires map projections, the mathematical process of converting 3D latitude and longitude into a flat 2D coordinate space. One approach is to have backend servers dynamically calculate and draw vector roads and labels on the fly based on a user's exact coordinates. However, generating dynamic vectors simultaneously for millions of users actively panning their screens carries an unsustainable CPU compute cost. Real-time server-side map rendering is computationally impossible at this scale, forcing us to move away from dynamic generation in favor of static pre-computation. The scalable alternative is to pre-compute the entire world map into static, predictable image slices ahead of time. We organize these slices by zoom level. Level 0 represents the entire global map in a single 256 by 256 pixel image. This quad tree data structure ensures that every increase in zoom level divides the previous tiles into 4 smaller, higher-resolution geographic bounds. The storage requirements are massive. The highest zoom level alone requires roughly 50 petabytes of data. Across all 21 zoom levels, including system buffers, the pre-computed map totals approximately 100 petabytes. By accepting a 100 petabyte storage footprint, we trade an impossible CPU rendering problem for a manageable and inexpensive storage problem. To serve these tiles globally with minimal latency, we utilize a content delivery network to cache data at edge nodes physically close to the mobile clients. With the images hosted on a CDN, the mobile client's only task is determining the exact URL string for the specific tile it needs. In a client-side generation model, the phone locally runs the geohash math to find its own grid ID. Alternatively, a server-side map tile service can take coordinates from the client and return the correct batch of CDN URLs. Client-side logic is faster but rigid, while an intermediary service allows the backend to update tile logic without requiring a mobile app update. Balancing client-side execution speed against server-side operational agility is a primary design decision in high-scale distributed systems. We must now resolve the 15 million peak query problem associated with updating the user's location on the map. Providing an instantaneous user experience does not actually require the backend infrastructure to receive a data update every single second. The user's phone uses local GPS hardware to move the blue dot instantly across pre-downloaded map tiles, requiring zero immediate validation from the server. This timeline graphic shows the client-side batching strategy. The phone buffers 15 seconds of location history and sends it to the server in a single efficient payload. This 15-to-1 compression reduces our peak database load from 15 million queries per second down to just 1 million. This batching strategy preserves client battery life and cellular bandwidth while neutralizing the write lock threat to our database. This diagram shows the finalized high-level architecture. The mobile client connects through a central load balancer to distribute incoming traffic. Batched location updates move through the location service and are stored in a horizontally scalable database. We use a distributed NoSQL database like Cassandra here to absorb the high-volume write workload. Navigation requests are handled by first querying a geocoding DB to convert textual addresses into coordinates, which are then passed to the navigation service. The navigation service calculates the optimal route using pre-processed routing tiles stored in high-speed object storage. By aggressively pre-computing nav tiles, batching location rights, and separating compute-heavy services, we have engineered an architecture capable of supporting 1 billion daily active users.